Okay, so today's last kind of review topic from Science 10 is on, I just coined it thermodynamics. I figured that was a pretty all-encompassing heading for what we're going to talk about today. The first slide is about the concept of systems. We're going to use systems in physics quite a bit. And so maybe, hopefully, taught all of you guys at some point, I think. You guys should know these terms, because we've used them before in some of my classes. There's the open system, the closed system, and the isolated system. You guys have heard these terms before? You remember them? So, kind of quick review. An open system would be like an open test tube. Right? Can stuff go in and out of it? Absolutely. Right? Our classroom right now is an open system. Can someone go in and out of the classroom? Yeah, why? Door's open. Hypothetically, I close the door. It's now considered to be a closed system because people cannot go in and out. Matter is not able to transfer within a closed system. So as soon as you cap it off, matter cannot go in and out. That's actually the main concept behind the open and closed. Matter cannot transfer here. Matter can transfer here. And what's an isolated system? Do you remember? It's all about energy. Good. Yeah, in this system here, energy doesn't even transfer. Okay. So the idea would be that no energy is ever lost to the outside surroundings. So this is supposed to kind of illustrate the concept of like insulation, I guess, in a way, of trying to prevent the escape of heat. Will heat always escape? Yeah, that's actually one of the rules we're going to talk about in a bit here. There's always going to be some loss of heat due to most likely friction. Friction is almost always the cause of some sort of loss of energy. That being said, we're going to most of the time assume that we're dealing with an isolated system because of the fact that it assumes that no energy is ever lost. But truth is that's probably not actually true. But we're going to assume isolated systems unless we have reason to believe otherwise. So because of this, if an isolated system means that energy is not really ever, I'm going to use my fingers for air quotes, but if we never lose energy, it means that mechanical energy is conserved. And you guys can just read this here, but essentially mechanical energy is the sum of all energies. If it's kinetic energy, if it's potential energy, I really don't care, but whatever energy we start with, we should have the same amount when we're done. We should finish. If we begin a scenario with 1,000 kilojoules, we should really end a scenario with 1,000 kilojoules. Nothing should be quote unquote lost. That's the goal. So it actually leads to kind of a new type of formula here, where whatever amount of potential you have, whatever amount of kinetic you have, this amount of starting energy should be the same when we're finished. Now, the amount of potential you have could convert into kinetic, or vice versa, but the total should be the same. Here's my written example here. Something falls. I said a rock. Let's use this lock. I hope I don't set the board too bad. Right now, what sort of energy does it have? Potential. As it fell, that potential converted into kinetic. And a split second before it hit the ground, really there was no more potential left, right? Because all of the potential had turned into kinetic. I actually have some animated diagrams on, not this slide, this slide. Is it actually going to work? Yeah, here it is. Okay, so imagine this scenario here. We'll let it play a few times here. You got a snowboarder going down the hill, I guess. I'll let it finish playing and then we'll talk about it the second time here. Okay, here we go. So at the very, very top of the hill, this guy has really only potential energy, right? As he's going down the hill, he's losing his potential energy. Where is his potential energy going? Well, it's turning into kinetic. Now, at the very, very bottom of the hill, though, why is this kinetic energy slowly but surely going down? Well, it's getting transferred into work. Work being done by the force of friction. Does that make sense? And so that's what's causing him to eventually stop. Right? But really, from here to here is the good analogy. As the kinetic energy bar goes up, the potential energy bar is going down. And right here, you'll see this bar. This is the total mechanical energy. It was always up there until eventually energy was, I'm using my fingers again, lost due to friction. Is it really lost, though? It's just converted to a different form, that's all. It's just lost because it's not useful anymore. This diagram here that was on the slide I skipped maybe can also be useful. As you ride up the hill, you use kinetic energy. So your kinetic energy bar is going down as you coast up the hill. Your potential energy bar is going up as you're at the top of the hill, right? And then as you roll back down the hill, the energy converts back to kinetic. This one kind of does the same thing here. Let's say that we have a little bit of both, right? Here it's total kinetic, then some kinetic, some potential as it goes around the loop-de-loop. Back down here, total kinetic. Some kinetic, some potential, totally kinetic. Loses a little kinetic to gain potential. That makes sense? At the end of the day, though, this bar right here, as long as we're assuming that it's an isolated system and nothing is being lost due to energy, then you guys get where I'm going here?
What's that stand for?
This one I think was supposed to be total mechanical energy. Mechanical energy is essentially a term we use for like all energy types. Usually the ones we care about are kinetic and potential, but I mean it could account for heat, light, sound. Does that make sense? Another one. Here's a bullet being shot. As the bullet's up in the air, there's some kinetic, some potential. I believe this is actually the potential due to a spring. We're kind of assuming that, I know a bullet isn't actually shot by a spring, but as it, basically think of a slingshot, as it gets pulled back, there's a whole bunch of potential due to the spring. That yellow bar immediately went down. It's slowly but surely turning into gravitational. So as the thing is going higher up in the air, you're getting more and more gravitational. And as the gravitational drops, then the kinetic regains again. Anyways, let's move on. Okay, so I mean, just like you asked here, mechanical energy or total mechanical energy is basically the sum of all of your energies. Sometimes we include thermal for friction, but normally we skip thermal for friction because we're assuming that no energy is lost, quote unquote, to thermal anyways, because we're thinking that it's an isolated system. Let's do some examples. Let's say that you have an object, 50 kilograms, and you drop it from 12 meters above the ground. How fast will it hit the ground? So I'm just going to kind of illustrate the scenario here. Imagine that you are standing on the top of, I don't know, some sort of building. Let's go up here. You have a heavy object. As you're on top of the building, what sort of energy do you have? For sure potential, right? We don't seem to be given any information about it currently being moving, so let's just assume that right here, all we have is potential. And then eventually the object will fall, right?
Please come to the office.
The split second before it hits the ground, it really doesn't have any potential anymore, right? Because it's right about to hit the ground. So at the end of it, really all we have is kinetic. In a way, we're going to now write our own formula. We're going to say that the energy potential that we started with before is now going to equal the kinetic energy that we're going to, I don't know, end with. I'm just kind of writing my own subscripts here. Whatever potential energy we start with before, all of it should turn into kinetic energy when we end. Will that actually be true? Not quite. Why? Friction, air resistance, right? You can actually see that based on different objects. We've learned that both of these objects should fall at the same rate, right? Why did this paper not fall at the same rate? Huge amount of air resistance, right? Just purely based on the aerodynamic structure of the piece of paper, there's a whole bunch of air resistance that caused it to kind of float its way down. So, that being said, so long as it's fairly aerodynamic, did this lock here probably pick up a lot of extra wind resistance as it fell through the air? Not all that much, right? Which is why when you're trying to design aerodynamic objects, like say missiles or spaceships or super awesome Ferraris, right? You're trying to make them as streamlined as possible to try to reduce the amount of drag there is. You know those terms? Okay. Anyways, let's keep working on this question then. What's the formula for potential energy, or maybe I should use a G here even. What's the formula for gravitational potential energy? Yeah. Mass times gravity times your change in height, however much happens to change. What's your formula for kinetic energy? Cool. This is where physics starts to go after a little while. what we're going to do is not just independently use all of the formulas on your sheet. Sometimes we're going to have to put them together. That was actually one of the questions on your test the other day. Brief aside, sorry, I sometimes scatterbrained you. There was a question where it told you that F equals ma, and then it asked you to try to find a new formula to go with it. You guys remember this question? And then the solution to it, if you haven't seen it, is that acceleration is actually velocity over time. So you can kind of take the velocity over time, plug it in there, and the final answer was mass times your velocity over your time. That's actually where physics starts to go at some point, where you don't just use one formula at a time. Often we take multiple formulas and find a way to make them equivalent to each other, and we make even more formulas. So there's like 80 formulas on that sheet. The possibilities are endless. We're going to take the gravitational energy and make it equivalent to the kinetic, and now we have a brand new formula. And we are solving for velocity. So let's plug in what we can. We know that a mass is 50 kilograms. We know gravity is 981 meters per second squared. We know that this thing's supposed to fall 12 meters. Then on the other side of the equation, the 1/2 is a constant. Mass gets plugged in for a second time, 50 kilograms. I'm kind of running out of room. And we need velocity squared. So with our new makeshift formula that we've kind of developed ourselves, hopefully you can see that, yeah, we have mass, we have gravity, we have height, we have mass. We don't have velocity, so I just need to have good algebra skills and rearrange for velocity. So, everyone does this a little bit differently. Myself, I times by 2 to get rid of the 1/2. And I would divide by 50 kilograms on both sides. You know what's kind of nifty about that 50 kilograms though? You can see how there's 50 on both the top and the bottom. If I really wanted to, not that you have to, but I mean, I could basically cancel this 50 kilograms with that 50 kilograms. Couldn't I? And it's on both sides. In a way, I could have done that in the previous step. See how there's an m on this side of the equation and an m on this side of the equation? If I really wanted to, I could have shortened up my equation and completely eliminated mass. Which kind of makes sense. Because you guys remember that story of Galileo dropping 2 cannonballs, right? Does the mass of the object actually impact how fast it's going? The answer was no, they both hit at the same time. So we actually can mathematically prove what Galileo knew hundreds of years ago, in that if the kinetic energy is going to come from the potential energy, and there's an m on both sides of the equation, you could actually cancel it out. We could have actually worked with the equation g delta h equals 1/2 v squared. Again, a large part of what we're going to be doing going forward is not just using formulas just off your formula sheet, but using them to make new formulas. Okay. Anyways, help me out here. Has anybody solved for what v is yet? Get a calculator. Don't forget to square root, by the way, right? There's that square root we need to do as well. 15.3? Anybody else get that? Okay, good enough. All right, units. You guys see here how there's a meters times another meters? If you square root it, you just have a single meter, right? Here you've got seconds squared, so if you square root it, you just have a single second. It asks for speed, so I think I'm good. I don't actually need to throw a direction. But if it did want to know the velocity, I would say that the direction is going down. How many of you have seen this before? Something like this. You guys remember doing this last year? Okay. So this is kind of our new challenge then for you guys in grade 12. Like I said, taking multiple formulas, putting them together, and making a further new formula. Let's try this one. Very, very similar scenario. You had a kid on the top of the balcony with a toy. The balcony's 19 meters above the ground, and the kid drops the toy. How fast will it hit the ground? This is the exact same scenario, isn't it? Right? Someone's up top here. Kinsey Ann's up top. She happens to drop her stuffy. She's going to cry when it hits the ground. It falls 19.2 meters. What did I not tell you this time around that I did last time? Yeah. But I don't need to know the mass, do I? Because mass doesn't matter. It cancels, right? So let's redo the work we just did just one more time. All of your kinetic energy that you get will have come from gravity. I don't think it matters which side the equation goes, right? Here I started with kinetic and ended with gravity, right? But essentially your kinetic came from gravitational energy. Kinetic is 1/2 of mv squared. Gravitational is mass times gravity times height. But we don't need to know the mass, because whatever that mass is, it's on both sides of the equation. Mathematically, it cancels. Someone help me out as soon as you're able to get me an answer.
19.
All right. Someone else gets an answer just to confirm that it's the same thing. You did? Cool. That makes sense. So, new challenge. You can't just work independently with each formula. I mean, you do need to know how to do that as well. But as part of problem solving, we may occasionally need to make our formulas equal each other. Essentially what we're doing is we're saying that E of any type is 1/2 mv squared. Another E happens to equal mgh, and we're making those bits equal to each other. Are there any other formulas that involve E on your data sheet? Yeah. If you take a look, you'll find probably lots of other ones. For example, there's one that goes E equals 1/2 of kx squared, I believe. Did I see what that one on there? Is it on there? E equals kx, 1/2 kx squared. Is that one on there? Yeah. So, I mean, even though you guys have no idea what k or x happen to stand for, I mean, that same logic applies. What we might end up doing at some point is saying that mgh equals 1/2 of kx squared. Right. I have no idea what k or x stand for, but doesn't that logic apply? At some point, maybe you'll learn how to rearrange a formula for mass. For example, force is equal to mass times acceleration. That's another formula on your data sheet. If I wanted to rearrange for mass, if I divide both sides by acceleration, I could say that mass is equal to force divided by acceleration. This means that I could take this m right here and write it as F over A times GH equals 1/2 kx squared. You guys get where I'm going here? Basically, you could do a series of substitutions and take one formula and substitute it into another, and we can make all sorts of crazy new formulas. Okay, let's move on. Another one here. Child shoots a Nerf gun, but here's the twist here. The kid is shooting the Nerf gun from the top floor of the house. Because of this, the gun is shooting at an initial speed of 3.6 meters per second. This is going to change things just slightly. Because now, when we're on top of our house here, and the guy is, do whatever it is we were doing in the past, normally it was just dropping the object. This one's a bit different though. This time around, he's actually using his Nerf gun, that's a gun, and he's launching it. It's not a big twist, but it's a little tweak. What sort of energy does the dart have when it begins then? Kinetic and potential. He is shooting the gun, so it has some motion when he begins with. So there is some kinetic as he begins. But he's also really high up in the air too, right? So because of that, it also has some gravitational energy. It has both. What sort of energy will it have when it hits the ground? Right before it hits the ground. Just kinetic. Right? Because the microsecond before it hits the ground, it no longer has any further distance to fall. So there's a bit of a twist here then. When we begin, I'll just kind of write it out like this. When we begin, the energy we have is kinetic energy. And we also have some gravitational energy. We'll have to sum up our energies. and find the mechanical energy of both. Find this total amount of energy we have to begin with. When this thing is finally about to end, all we'll have left is kinetic. So in a way, I'm starting a new formula, a brand new one, not the same one we did last time where it was like V 1/2 of V squared equals GH. This one's going to be slightly different. All right, well, this will be 1/2 of mv squared. This will be mg delta H. And this will be 1/2 of mv squared. I would really recommend, though, this is my personal preference. If you need to, sometimes it's worthwhile to put a little subscript in the bottom corner just to keep track of things. For example, this mass right here, will it ever change? I don't think so. But will the velocity change? Okay, so why don't I go with velocity B, just for velocity before, just to kind of keep them straight. And then over here, when I do this velocity, I'll go with velocity after. I mean, you can pick 1s and 2s, A's and B's, smiley faces and stars. I don't really care, right? But sometimes it's a good idea just to put a little subscript to kind of keep track of them when there's more than one, because this starting velocity will be different than this final velocity. Maybe we could even use I's and F's even, right? I was given the mass, 12 grams right here. Was it relevant though? Is there a way for me to cancel mass? I actually have 3 terms, right? Is mass in all 3 of the terms? Then yes, I can cancel mass, but let me show you the reason why. What we're going to do is we're going to take these 2 terms right here, and we're going to use the math skill of factoring. This is why we're doing this in math right now as well. What can I factor out of this side of the equation here? What's the only thing common? Mass, yeah. So if I do that, I can factor out mass, and then open up a new bracket. And what it would leave is a 1/2 of my before velocity squared, and g delta H. Because mass is on both sides here, both terms. Could I then divide both sides by mass and completely cancel it out? Yeah, absolutely, right? So I could essentially get rid of mass and get rid of mass, and now I've made myself a new equation. 1/2, no more mass anymore, mass wasn't relevant, of our velocity before squared plus gravity and height should equal 1/2 of my velocity afterwards squared. If you guys want to, you probably could have just canceled mass here, here, and here. That would have been valid if you wanted to. But I just wanted to show you the overlap of factoring. So, okay, let's plug in numbers. Do we know the velocity before? Before it started, it was 3.6 meters per second. Gravity, 981 meters per second squared. The one thing we don't know is our change in height. So I guess I have to leave that as a letter still. Our velocity afterwards, when it hit the ground, it had sped up. 8.2. And now it's just really a math problem. How do you get this h by itself? Mathematically, what needs to get moved? This stuff right here does. How are we going to mathematically move this stuff here? What's it separated by? A plus sign, right? So I'm going to need to subtract 1/2 of 3.6 meters per second squared. So over here we're going to have to subtract 1/2 of 3.6 meters per second squared. That's how we'll get rid of this little bit right here. I have to subtract that bit away. Can these two things subtract from each other? Do they have compatible units? Yeah, right? This one is in meters per second squared. This one here is also in meters per second squared. So someone give me a hand here. Has anyone actually calculated what this will be when you just subtract those ones? 1/2 of 8.2 squared minus 1/2 of 3.6 squared. Say that again? 12.6? 4.6, okay. And that number still has more digits, I'm thinking, right? Oh, it's straight up, it was just 4.6. Okay. Anybody else get that too? Okay, I should check it. Okay, calculator. 1/2 of 8.2 squared minus 1/2 of 3.6 squared. I got 2714. Anybody else do what I did? Yeah? Sorry, Andy. Okay. Thanks for being brave. You actually offered something. Okay, 2714 then. Where are we here? There we go. So let's get rid of that. Not 4.6. 2714. The units then would be meters squared over seconds squared. Does that make sense? Because we're squaring both of those two. Right, last step, we do need to get this delta H by itself. So we're going to need to divide by 9.81. So maybe some of you have already kind of gotten to that point. If we divide by 9.81 meters per second squared, I just want to show you how the units are going to work out here. This second squared and that second squared will cancel. And this meters squared, there's essentially two of them there, right? One of them will cancel with that meters. So I need to take the 2714 number that I just calculated and divide by 9.81. And then just hit up the sig digs properly. So 2 sig digs, 2.8 meters high. Quick recap of what we did then. It was a bit of a change. Our formula was not quite the same as it was last time because we had two types of energy to begin with, kinetic and potential for gravity. And we end with kinetic. This was still nifty though. Mass did still cancel, which makes sense because you've hopefully heard at some point that mass really is irrelevant in some of these calculations. So we canceled out mass. We made ourselves a brand new equation, which probably is best written right about here. We then plugged in a whole bunch of values, and we just had to isolate for the h. So this term we had to subtract away, and then this term we had to divide away. And there we go, our answer. That makes sense? Okay, one last thought here. This all assumes something, though. We assume that all of our potential energy converted to kinetic, but what if it doesn't? What if we intend for all of this to turn into this, but only part of it does? And that's where the term efficiency comes in. Most systems or machines are not 100% efficient. If it's an isolated system, though, we are going to assume that everything is going to transfer. But we need to recognize that in real life, that's not how things work, right? We are going to lose, and I'm using the word lose like in quotes, right? Because the energy is not really lost. It's just not considered useful energy. But we're going to lose some energy to probably friction, heat, light, sound, whatever it is, right? So really, efficiency is just like a percentage, right? You find out how much output you got, you divide by how much input you got, times by 100. And that's your percent efficiency. So, do I have an example? No, I don't. Let's just make one up real quick, because this is like the easiest thing in the world. Let's say that when you started, way up here on the top of the building, you had 31 joules of energy total. And then you shot your Nerf dart. And when it landed, it only had 30 joules of energy. Is that normal? Yeah, I think so, right? Where did the extra 1 joule of energy go? Heat, friction, maybe sound. Something along those lines, right? So if I wanted you to calculate your efficiency, you would take 30, divide by 31, and times by 100. I mean, it's a really straightforward formula, right? You take your output, you divide by your input, and you times it by 100. And whatever that would be, right? This would be a very efficient system, right? Because you really didn't lose that much due to energy, or due to friction. There are some systems that are incredibly inefficient. For example, you guys know like the old school light bulbs compared to like these newer ones? Well, those old school light bulbs, like they heat up like crazy. We have one in our the top of our pantry, and Melissa put her baking stuff on the very top shelf, and it completely melted all of her chocolate chips, right? The light was left on overnight, right? Is a light bulb supposed to give off that much heat? Well, that's not its intended design, right? Its intended design is just to give off light. But unfortunately, it's a very inefficient light bulb. It burns really hot, so it melted all of our chocolate chips, right? These newer light bulbs, whatever they are, fluorescent ones, incandescent, I don't remember the difference between the terms, right? But these newer ones, they're way more efficient, right? That's the idea. So, that makes sense to you guys? Okay, last slides here. All of what we've been talking about here then is actually based on what the topic of the day is. It's called the laws of thermodynamics. And so I want to either introduce you or reintroduce you to these two laws of thermodynamics. And basically, I'm not going to be testing you on this probably past tomorrow. This is actually really more Science 10 curriculum, the thermodynamic stuff. But I think it's worth mentioning just because of how it fits into the topic of making new formulas. So here's the law. The first law of thermodynamics basically says that the total amount of energy is constant. Whatever energy you had before is the exact same after. There should be no more. You can't start with 10 joules and somehow get 11 afterwards. I've sometimes heard the laws of thermodynamics explained in terms of gambling. And this one makes sense to me, so I'll share the same thing with you guys. Vegas never loses. The house always wins. So in a way, if you go into Vegas with $100, you're not coming out with 105. Vegas is going to steal your money from you. Does that make sense? The law basically says whatever you start before with, the law says that it remains constant. And in a way, sometimes it means that you can't actually ever get more. It's not possible for you to get more. A perpetual motion machine is this hypothetical device that would run for forever. Basically, the idea is once you get it started, it will always just keep going. The amount of energy would be constant. But we know that to be completely impossible due to our second law of thermodynamics, which states that heat and energy always goes from hot objects to cold ones. In a way, this law states that you're always going to lose some energy. So if you want to use that Vegas analogy, the first law of thermodynamics says that you're never going to get ahead. You can't start with 100 and get more than that. The second law says you're actually always guaranteed to come out a little bit lower than you started with. I don't care how aerodynamic you make your missile, it is going to lose a little bit of energy due to friction. It has to. Does that make sense? Because, like it says here, energy always flows from hot objects to colder objects. Right? And so it's going to lose that energy and dissipate out into the surroundings. As much as we would like to start with 100 joules and end with 100 joules, there will always be at least a little bit that kind of gets lost. So one more time. First law, in basic terms, is if you start with 100, don't expect to get to 101. Energy does not just magically show up out of nowhere. Further, that second law says if you start with 100 joules, expect to at least lose something, depending on how inefficient the machine is. That being said, for us in our calculations, we are going to assume an isolated system, which means that if we start with 100 joules, we're going to assume that we do end with 100 joules, but we're just going to know going in that due to air resistance, drag, friction, all those sorts of things, that our answers will probably not be quite truthful in a real life scenario. So when we end up doing a lab where we try to calculate, we're actually going to do one where we shoot a Nerf gun, probably in the atrium because there's enough room here, and we'll try to calculate how far it travels. We're going to expect that it's going to go this far, based on our calculations, but it'll probably only go that far because there will be a little bit of air resistance on it. Does that make sense? Okay. So let me summarize. That was our last slide. Second last slide? Third last slide? Second last slide. Oh, okay. I forgot. It is actually possible, technically, to move heat from cold to hot, but it's an air conditioner, essentially, is what you're doing, right? And so, although you might argue, hey, hang on, you can actually have heat go kind of backwards, you have to do work to do it, right? I put this picture on here because as an air conditioner is spitting out cold air, it's not just spitting out cold air without nothing else compensating. You guys ever worked with one of these air conditioners before? You have to have the hose running outside because what is this hose for? Yeah, and it spits the hot air outside. Does that make sense? So really, in a way, the system is still complete. However much energy in terms of like negative cooler energy, I know that's not really true, but like in terms of how much cold there is right here, there would be an equal and opposite amount on the other side when we get spit out. If you had one of these air conditioners and you left this tube going back this way, it would do nothing, right? Because this would be spitting out some cold air and this would be re-spitting out the hot air as the heat is being removed from your house. Essentially, that's what an air conditioner does, right? It removes the heat from your house and spits it outside. The absence of heat is cold. There really is no such thing as cold. Cold just means that you're lacking heat. So if you can find a way to send the heat outside, then you'll feel cold. Anyways, I just wanted to point that one out because sometimes people think that it's not. This might not be true. They're like, hang on, I can make things colder. Heat doesn't always go from hot to cold, but really that's only because you have an air conditioner, and it's really just a clever design. Okay, so here's what I need you guys to be able to do. In terms of energy, I need you to be able to handle the type of scenario where you're doing something like shooting a Nerf gun off the top of a bridge. Or you're just dropping an object, where you take formulas and you need to take the 2 or 3 possible formulas and meld them together and make your own. The good news is mass almost always, I can't think of a scenario right now that you'll encounter, but mass will always cancel. Right? It should. And then you just have to have good algebra skills to rearrange. But that's this little bit right here where you have to make your own formulas. This little section here. I would like you to know the basics of first and second laws of thermodynamics. So first law, don't expect to get ahead. That's not possible. Second law, expect to actually lose a little bit even. So gambling terms, you're not going to beat Vegas. The best you can hope for is to break even. Second law, you're not actually going to break even. You're going to lose money. That's kind of the correlation. And you should know how to do efficiency. Okay. Questions, comments, concerns, conundrums, curiosities, complaints, criticisms. I'm running out of those words. What are those words? Is there any questions? Yeah.
What's the point of going to Vegas if you're just going to lose money?
It's fun. I don't know. Yeah, I mean, actually in Vegas, some people do win money, obviously, right? But as a whole, this is where Vegas makes all their money, right? Is like 99 people all lose money, and sure, there's one person who actually comes out ahead, right? And so then you think I could win, but really most people actually come out busted, right? So. Okay, we have about half an hour left today. If I can give you guys some advice, it may actually be, believe it or not, start on your first kinematics assignment. You might not be able to do all of it yet. Where is it? Oh, I need to get to the website here. But that may actually be the best thing to start on, is start trying some of these questions. Obviously, you're going to want to skip the first one on graphing because we actually haven't talked about graphing. But you may be able to solve some of these other questions here because you know a good chunk of the kinematics equations already. We haven't covered a few of them, but at some point, really, as long as you know how to plug numbers into an equation, that's kind of where we're going here. So tomorrow we're going to do another take on the test though. Okay. Again, it doesn't count for anything. It's just really meant to be give you a chance to see what assessments look like, see the difficulty of the questions we're going to solve.
So what's testing?
Yeah, just the same, more of the same.
So
Basically, just another try at it, right? So, I mean, there will be what we talked about today, Andy. I'll put some questions on there on that. Okay, but really, it's just more of what we did last time. Just another shot at it. That's all. That's what I would use. There's supposed to be one in the senior high area too, though, apparently. So.
yeah, it's in that like this clear room.
Yeah, it's in that room over there somewhere. Okay, I'll stop the recording. If you guys want to take a 5-minute break just to get up and move, feel free. And then, yeah, you got about half an hour to do something for the rest of the class.